Hello, we're going to be focusing on the second order linear differential equations, where we have constant coefficients. And particularly, we're going to focus on the case where our characteristic equation has repeated roots and why the solution we get is the one that works. So if I have a second order linear differential equation, which is y double prime plus p y prime plus q qy equals 0, with p and q real constants. We saw that we could get three different cases. We could get, when we look at our characteristic equation, our lambdas could be two distinct and real. We could get two complex, or we could get this case where when I factor this, or if I end up using our quadratic formula, my discriminant equals 0. So my p squared minus 4q is 0 in this case, and I'm left with minus p over 2 as my lambda. So this is the repeated root case. So we saw that we end up having solutions of the form y of t equals some constant e to the minus pt over 2 plus t with some other constant. This is constant 1, constant 2, e to the minus pt over 2. When I did this example in class, I said, just trust me on this t. But now I'm going to go through how we actually get that t. So keep in mind that we know that one of our solutions is going to be e to the lambda t. And we want a solution that is not the constant multiple of y1, because we want linear independence for my solutions. So the method that we can look at to find the second solution is similar to how we ended up finding the inhomogeneous solution for our first order differential equations, where we assume that we have some unknown function v of t times y1, which was our homogeneous solution. In this case, this is just the first solution that we have. And here we're going to specify that v of t is not a constant function. So it does depend on t. We know that it's not constant, or else we're not going to have linear independence of our two solutions. So this means that y2 is going to be of the form v of t times e to the minus pt over 2. So let's plug into our differential equation. And see if that can give us some information about what it means for this function y2 to be a solution. So just a reminder that our differential equation is y double prime plus p y prime plus q. And I'm going to replace that q with p squared. So I'll show you where that's coming from in a moment. But p squared over 4 times y. Sorry, my y's have dropped out. But that is coming from the fact that I know since this is a repeated roots case that my discriminant p squared minus 4q is 0, which means that p squared equals 4q and p equals, and q equals p squared over 4. So since I know that relationship between P and Q, I'm going to use that relationship here so that I only have to worry about P and I don't have to worry about two different variables or two different constants in this case. And this will also help me get some simplification when I plug in my Y2 because there's no Q in my Y2 right now. All right, so if I plug this in, I'm going to get a second derivative of y2. So a second derivative of v of t e to the minus pt over 2, and then plus p, I get first derivative here. And that's going to be also of my function e to the v times e to the minus pt over 2. And I'm writing out v of t explicitly right now because I want to make it clear when taking these derivatives that we do have to take a derivative of v as well. We don't want to confuse it and think of it as a constant right now. It is a function of t. And this all equals 0. Okay, so let's do out our derivatives one at a time so that we don't get lost in the weeds. It's very easy to, make mistakes with doing multiple steps at once. So if we take one derivative of our v of t times our exponential function, we can just use the product rule. So I'm going to say this is v. Now that I'm taking derivatives of v, I'm going to drop the of t just for space. So we take the derivative of the first and multiply it by the second. And then we can do the reverse. So keep the first as is and take the derivative of the second. Okay, so that's one derivative so far. And now we can see that taking one derivative of the same thing, we're going to get the same thing, which is good because it saves us a little time here. pt over 2 minus v pt e to the minus pt over 2. Gonna put that away in there. And then I have my plus p squared over 4 v e to the minus pt over 2. And for this to be a solution, all of this has to be 0. Okay, so now I'm going to do my second derivative from that first term. So I'm going to, again, do product rule on each term. And in this case, I have v double prime e to the minus pt over 2. Then I get minus v prime, and now I have to take the derivative of that exponential. So I get p over 2 e to the minus pt over 2. And now I have to take the derivative of that second term. I'm going to keep a minus out in front just so I don't have to worry about that minus. But we again take the derivative of v, and I'm going to keep everything else as is, pt over 2, e to the minus pt over 2. And now I'm going to keep v as is and take the derivative of the exponential, which gives us that minus p over 2. And this is now going to be squared because we get an extra factor of that p over 2 from that derivative of the exponential. Okay. So then we have done out that second derivative. We're going to have to do a little bit of, collecting terms here, but that's okay. Since I'm done with derivatives, I'm going to just distribute the p, and I'm going to keep everything else in black. The black was just to show, what part I was focusing on when it came time for those derivatives. Okay, so if I distribute that, I get this minus pt over 2, and then minus p squared over 2 times my v, e to the minus pt over 2, and then plus p squared over 4, v e to the minus pt over 2 equals 0. All right, let's continue collecting those terms. So this is our only v double prime. So it's safe to say I can just leave that as is, as my top term right here. Next, I'm going to look for all of my v prime terms and make sure I have all, correct coefficients here. Let's see, I believe that's it for my v prime terms. Okay, so it looks like I have a 2 minus v prime p over 2 e to the minus pt over 2. So let me combine those first. So I get minus v prime p, the 1/2 cancel with each other because they add up to 1. Right, so e to the minus pt over 2, and then we get a plus from that third term, v prime p e to the minus pt over 2. And that's pretty nice because that means that those terms are just going to cancel. Okay, and then last we have to look at our v terms, and we want to be careful with our coefficients again. So we have this negative that gets distributed to that first term. So if we do that, we can see that we have a plus v p squared over 2 e to the minus pt over 2. And then we have, so then we have a minus p squared over 2 v e to the minus pt over 2, and a plus p squared over 4 v e to the minus pt over 4. So one thing I'm seeing here is I'm seeing that I have essentially 1/2 v p squared e minus pt over 2, and minus 1/2. So those look like they're going to cancel. That's nice. And then I'm left with this p squared over, yes, I'm left with this p squared over 4 term. Sorry, I made a little mistake. So one thing to be careful about, that I wasn't careful about for a brief moment was that this p over 2, that whole thing is squared. So this first term is actually a minus, which one am I? Okay, so this first term that I wrote down for my V's right here, this first term is actually a p squared over 4. So just that's why we should be a little bit careful. I probably could have taken some more steps in between there and checked that to make sure that was going to work out. Okay, so we can combine this term and this term here. We get this 1/4 and 1/4 of the same term. That's going to give us 1/2, right, of p squared v e to the minus pt over 2. And that is going to cancel with my p squared over 2 v e to the minus pt over 2. So those three terms together end up canceling. So we started with something that was pretty complicated, but we actually end up getting something that's not as complicated in the end. We get the second derivative of our unknown function times this exponential equals 0. And one thing that we know is that this exponential is not 0. The only time this is going to be 0 is if we take t to be infinity, but for any sort of number that we're going to be plugging in, it's not going to be 0. So that means if I have the product of two things being 0 and one of them's not 0, that means that v double prime has to equal 0. So the question now that we have to ask is, what is 0 after two derivatives? So what sort of function is 0? And we can think of the function that is a equation of a line, right? So with constants a and b, if I take the derivative of my v, you can see that I'm just going to get a, and if I get the second derivative of that, I'm just going to get 0. So we solved it. We found what v must be. So since a and b are constants, we could keep v of t as at plus b. And if I do that, so remember, we're trying to find our solution 2 here, which we said was v of t times e to the minus pt over 2. And we had y1 as e to the minus pt over 2. So if I keep that b in there, what's going to happen is it's going to combine with my with my y1 once I add in and get my general equation. We are going to just have some constant multiple of y1. We don't need another one of that. We can just can choose b to be 0 because it's not giving us anything extra. And in this case, since when we talk about our fundamental set of solutions, we don't have any constants out in front. Those constants come up when we have our general solutions. So I'm just going to choose a to be 1 in this case. So I have y of 2 equals equals 1 t e to the minus pt over 2. And then when I have my general solution, I have some c1 e to the minus pt over 2 plus c2 e to the c2t e to the minus pt over 2. And I can pull out those exponentials just to clean things up a little bit. And I get that my general solution for this case is c1 plus c2t all times e to the minus pt over 2.